Hi. I'm Lenka Schnaubert and this is Eric Andre, and I'm going to talk today about global self-evaluations and local self-evaluations and their impact on behavior. And the background of this research is the project Adaptive Tutoring Feedback, which is a cooperation of the SALTech, which is represented by Eric Anders today, and the Dresden University of Technology, which is represented by me, and the project is funded by the German Research Foundation. The project aims at enriching a computer-based learning environment with tutoring feedback components and to adapt them to learner as well as task characteristics, and all of this within the domain of fraction learning, because this is a really difficult domain for students like 6th or 7th graders. When they learn to handle rational numbers, they can't apply all the concepts and rules they've learned from the natural numbers. So this is the background. So first, a few words about adaptation. Adaptive instruction can be perceived as having a tripartite nature. So we have the source of adaptation, which could be learner characteristics or task characteristics, or of course the interaction of the learner with the system. And the target of adaptation, which can be a variety of things, but in our case, of course, it's a feedback project. The target of adaptation is the tutoring feedback and the transition from source into target. So that's to adapt instructional components such as the feedback, we need to answer a few questions. One of them being identify these relevant learner characteristics and study their impact on critical learning behavior. But of course we also need to look at the influence of the instructional elements, or in our case feedback, on the learning behavior and their interaction to develop and evaluate adaptation algorithms. And today we're going to focus on the first part, namely identifying those learner characteristics or study their impact on learning behavior. So in previous research within the project, we found that self-evaluation are critical for the learning behavior. For example, we found that global perceptions of competencies, so how students evaluate their own competence within the domain of fraction learning, have an impact on learning behavior. So students who perceive their competence to be comparably high show different behavioral patterns than those who perceive their competence to be comparably low. And these behavioral patterns differ with regard to achievement and motivation, and this, of course, we are not the only ones who found this. This is in line with other research. Well, we also did find that local confidence judgments have an impact on the following behavior. So students with a high response confidence, if they conduct an error with a high confidence in their answer being correct, after they get fed back that their answer was erroneous, they behave differently than those who didn't have a high confidence in their error. And this is in line with the hypercorrection research around Metcalf. Of course, there are other researchers looking at this also, who found that errors committed with high confidence in their correctness are hypercorrected. And also this is in line with feedback research on Behaviour, for example, who found a motivational impact on the following behavior if there was a high confidence error. So let me compare shortly these two concepts. They both are kind of self-evaluations, but of course they're really different. So the focus of perception of competence is it's domain specific, while response confidence really refers to a certain task. And while perception of competence, the student evaluates their competence, response confidence is performance-based and, as I said, task-specific. So usually perception of competence is assessed via questionnaire data, for example, prior learning phases, and response confidence is always online, assessed again and again within the learning task. So perception of competence also of course more static, while response confidence, the student can really react to difficulties he or she perceives while working on a learning task. So response confidence is a local measure and should account for inter-individual differences also, while perception of competence can only account for inter-individual measure differences. So it should be more appropriate to predict local behavior, but we have always a problem with confidence measures, because first it requires repeated judgments, and whoever of you has been in a learning environment where they ask metacognitive judgments again and again and again and again, students get really annoyed with this, so the reliability of these judgments is not always that high. And also the students always have to switch between content-related and content-unrelated tasks. That means when they're working on a learning task and they're working with fractions, and then they are asked, how confident are you that your answer is correct? They have to go on a metacognitive level and think about their answer, and then go back into the next task or the same task and back out again. So the question is kind of, is it worth the hassle? Is response confidence so much better that we really need such measures and cannot rely on more global measures? Therefore, the aims of this are to compare response confidence and perception of competence predictive power for critical post-error behavior. And if we're looking at critical post-error behavior, we of course first have to define what we perceive as critical behavior. So we, for our studies, define behavior as the interaction of the learner with the learning environment, because this is when the student tells the system what he's doing. And he's usually doing this by collecting inputs, which can be evaluated online by the system. So we define dimensions of behavior as characteristics of the inputs of students within learning tasks, because we were working with a learning task-based environment. And there are two dimensions we want to focus at, one of them being the quality of the input. So in a learning task, of course, the student can solve the learning task correctly. So is the input correct with regard to the learning task, which is a performance measure, formative assessment, and solving indicates, of course, that the student has a certain ability. And we will also be looking at the quantity of input. That means if a student provides a possible solution to a problem or not. Because within the learning task, we can see it, especially if we're giving tutoring feedback, which becomes more elaborated, usually step by step, and in the end, the students get the answers to the learning task. They just click next, 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 and do not engage in the task at all, and therefore this is an important dimension also. Of course, there's another dimension of inputs. We have the timing of inputs, but we won't be looking at this today. So back to the research questions, we wanted to know if we can, if critical post-error behavior can be predicted using perception of competence or response confidence with regard to their quality and their quantity, and of course, if any of those superior. And how we did this, Eric Andres will tell you, and I'll be back for the results.
So I'll give you a brief rundown of what we did to get our hands on the data we analyzed. So the working environment we exposed the students to was active math based. Active math is an intelligent learning environment for mathematics, in particular also able to cope with fractions. And why it's a good choice for this particular project is that it's able to run all kinds of exercises, multi-step, single step with scripted feedback, so we can very easily implement very special type of exercise at the end. And also, it has a connection to a computer algebra system on the back end, so it can evaluate all different kinds of aspects of the correctness of the solution, which is relevant for this because we want to actually see did they solve it or not, so we have to recognize it automatically. And in particular, we need to, for instance, also differentiate between 1/3 and 2/6. These are particular kind of equivalence is different from 1/3 equals 1/3 is different from 1/3 equals 0.33. So we exposed 101 students to this thing. They were invited to the University of Technology Dresden in groups of about 10 people, and they worked on 8 learning tasks on the system. And so we took a task sample that is balanced with regard to learner and tasks, which means that so we had 101 learners. They worked on all the 8 tasks. They were working kind of self-paced. And while they were working on these exercises, they were tutored by hints and explanations. This is the procedure of the experiment that we did. So first, we gave a pre-questionnaire, a little pre-test, a standard design intervention, a post-test, and a post-questionnaire. We only focus on two phases of the experiment here. So the first phase is the pre-questionnaire, and as Lenka already told, this is the place where we assess perception of competence measures. Then during the intervention, we do two other things. We take response confidence and we get our behavior. I will go into a bit more detail of how we collected this now. So the perception of competence score was built on a scale that was already there from Professor Narciss. And we used three items that made a statement like, I think my performance regarding fraction task is very good, it's domain bound, and they had to answer this on a 6-point rating scale. The Cronbach's alpha was fairly high, so we could use this information, and we built an arithmetic average to compute perception of competence score, which ranged from 0 to 100. Response confidence was assessed while we were working on the task, and it was only assessed in the first step of the task. So it was a question, how confident are you that you solved the task correctly? And they used a slider widget, which while they manipulated it, it showed them the value that they actually selected, and it also ranged between from 0 to 100. So with behavior, it's a little bit more complicated. I have to briefly explain what kind of tasks we administrate to students. These were tasks with typical errors. So basically, these are worked out examples which contain frequently occurring errors. And these are, well, they are extracted from pen and paper tests which students build out. And so it's really typical error. From this, we build the exercises in two phases. The first phase is that the students have to detect the error. So that would be one of the exercises the students were presented with. It's like Excel should have computed some of fraction, and this is how it proceeded. He did something wrong in this particular case. This was the erroneous step. They cancelled in the sum here. So if the student spots this, they just select it and go on to the error correction step. If they get it wrong, then they get the feedback where the error was to ensure that everybody tries to correct the same error. And once they know where the error is, they are asked to correct it. And we have developed a kind of interesting interface for that, which allows them to continue in several directions. They have to correct it. They get 3 trials to solve this task. So once they select it, they get tutoring feedback, and then they can try again. If they get it right, they just can go on to the next task. This initial trial kind of helps us to find which students actually need help within these tasks. So we are focusing on trials 2 and 3. That's our post-error behavior. So this is one of the states of an exercise after an initial error. So here they tried to correct something. It was wrong. They got this hint, and then they can try again. This selection process, by looking at only post-error behavior, slightly modified our N. So we only have 330 tasks which contain an initial error, actually. So based on this sample, we then coded our 2 variables, quality of input, namely was it correct or not, and quantity of input, did they provide a solution or not. And by this, we just looked at, did they try to do anything in the interface? As soon as they manipulated something, it was considered not a skip anymore. If they didn't manipulate anything, it was a skip. So this gives us our variables which we're interested in, so our continuous variables, response confidence and perception of competence, and the binary things we want to predict, namely, did they solve it or not, or did they skip or not? And to analyze this, we conducted a logistic regression analysis, which now Lenka will present again.
Okay, as promised, I'm back for the result. These are the regression models we computed. First of all, for solving behavior, the first you can see is the intercept-only model or the null model, and the next two models are the models containing response confidence or perception of competence. And what we can see here that response confidence as well as perception of competence have a positive influence on the solving behavior. So the higher the confidence, the higher the solving rate afterwards, and the higher the perception of competence, the higher the solving rate also. And with regard to skipping, we have the formulas here, and we can see the negative influence that is because the skip was coded 1 if there was a skip. So that means the higher the confidence, the lower the chance of skipping. And the same with perception of competence. And what we can see is that the p-value here for response confidence always are slightly higher than for perception of competence. So I'm aware that we probably can't read all this, so I'll just point out the most important things. So what we can see here is that for solving response confidence, the regression coefficient for response confidence is significantly different from 0, but this is not the case for perception of competence. And for the skipping model, it's the same. And we can also see, I won't go too much into the detail, but we can also see that the response confidence model is always significantly better than the null model or the intercept-only model, whereas the perception of competency model isn't. So if we're looking at the cross tables for the observed values and the predicted values, so we can see the observed values here. So for solving this is the non-solved, so 258 in 258 cases the students were not able to solve after initial error, and in 72 cases there were, so the solving rate was quite low. And we can see that all the models predict the same. They always predict a non-solved. So for the intercept-only model, that's clear because they only have the data to go from. So they say if they solve less than they do solve, we always predict a non-solve, and that's the best bet. And for the perception of competency model, we are also not surprised because it's not significantly better than the null model. But for the response confidence model, we are kind of surprised, so we looked into it. So if we look at the formula again, we can see the constant with minus 2.3 is quite high. And if we remember that the scale from confidence was from 0 to 100, so even if we take the maximum value at response confidence of 100, we still have 2.3 minus 1.9, which is minus 2.3 plus 1.9, which is still a negative value, which is still a prediction of a non-solve. So that's why the models here don't predict anything different, and the accuracy is 80%, but that's only because 80% did not solve afterwards. For the skipping models, the cross tables actually do differ, which is nice. They really do differ this time. And we can see that the null model, the intercept-only model, of course, is not as good here because kind of half of the people skipped and half of the people didn't. The perception of competency model is not really different from the null model, and the confidence model is just slightly better. So but it's still far from perfect. So it can predict a few non-skips more, but it's still not as good as we would like it to be. So to sum this up, the confidence models were significantly better than the null models and increased the accuracy of prediction for skipping, but not for solving. But still, the models were not really good. The perception of competency models have not shown better than the null models, neither for solving nor for skipping, and the impact of the predictors was altogether rather small. So our global parameter might account for general behavioral strategies because we found this over and over again, but it's not sufficient to really, if we really want to look at local behavior and predict this. And despite the difficulties we often have if we use repeated confidence measure, we need some local measures which can account for intra-individual differences also. If it's response confidence, it wasn't so good results that we would say we really have to go for this, but at least there is the prediction increase. So maybe you should take previous behavior into account or task characteristics. In preliminary analysis, we found, for example, the skipping rate differed very much from the task characteristics. So, for example, the task for adding fractions without a common denominator, the skipping rate afterwards was about 75%, whereas for easier tasks it was only 25%. So we should take this into account, and actually that's what we are doing just now to enhance the models with task characteristics. And of course we were talking about predictions, but what we didn't check this on a different sample now. So that would be the next thing. If we have a model, a better model, hopefully, than this, to test this on a different sample. And of course we want to include feedback, because this is a feedback project and this is our potential target of adaptation, and we are onto this right now to look at the interaction between the learner characteristics and the feedback provided, and of course the task characteristics. So thank you very much for your attention.